And you might wonder, are we alone? What kinds of worlds orbit the billions of stars in our galaxy? For centuries, we only knew the planets in our own solar system, small, rocky worlds like Earth gas giants like Jupiter and ice giants like Neptune. But over the past 30 years, a revolution in space exploration has uncovered something extraordinary, a whole class of planets that exist nowhere in our solar system, worlds that bridge the gap between our home planet and the icy giants at the edge of our system. These are super-Earths, the most abundant, diverse and fascinating exoplanets we have ever found. Today, we are going to journey deep into the cosmos to explore these alien worlds, understand what makes them unique, how we discovered them, and why they are the key to answering one of humanity's greatest questions. Could there be life beyond Earth? First, let us start with the basics. What exactly is a super-Earth? You might think the name means a better or more habitable version of Earth, but that is not the case at all. The term super-Earth is purely a description of size and mass, nothing more. A super-Earth is an exoplanet, a planet outside our solar system, with a mass between 1 and 10 times that of Earth, and a radius between 1.25 and 2.5 times Earth radius. This places them firmly between two categories: the small, rocky, terrestrial planets like Earth, Mars, Venus, and Mercury, and the much larger ice giants like Neptune and Uranus, which are about 14 to 17 times Earth's mass. There is no planet like this in our solar system, which makes them even more mysterious and exciting to study. They are not gas giants, they are not tiny rocky worlds. They are a cosmic middle child that has rewritten the rulebook of planetary science. The story of super-Earths begins with one of the greatest breakthroughs in modern astronomy: the first confirmed discovery of exoplanets. Before the 1990s, we had no concrete proof that planets existed around other stars. All we had were theories and guesses. Then, in the early 2000s, astronomers started using two powerful techniques to hunt for exoplanets: the radial velocity method, which measures the tiny wobble of a star caused by the gravitational pull of an orbiting planet, and the transit method, which detects the faint dip in a star's brightness when a planet crosses in front of it. These tools changed everything, and in 2005, astronomers made history by finding the first confirmed super-Earth Gliese 876d, orbiting a red dwarf star just 15 light-years from Earth. This planet was about 7.5 times Earth's mass, and it opened the floodgates for thousands more super-Earth discoveries in the years that followed. Then came NASA's Kepler Space Telescope, launched in 2009, which became the single most important tool for finding super-Earths. Kepler stared at more than 150,000 stars in a single patch of the sky, looking for the tiny transit dips that signal a planet. Over its 9-year mission, Kepler discovered thousands of exoplanets, and nearly half of them were super-Earths. It found worlds like Kepler 62Fa, super-Earth in the habitable zone of its star, 1.6 times Earth radius, and Kepler 22b, the first super-Earth found in the habitable zone of a Sun-like star. These discoveries proved that super-Earths are not rare, they are everywhere. In fact, astronomers now estimate that super-Earths orbit nearly 30% of all Sun-like stars in the Milky Way, making them the most common type of planet in our galaxy. That is a staggering number, and it means these worlds are a fundamental part of how planetary systems form and evolve. Now let's talk about what these super-Earths are actually made of. Unlike Earth, which has a fixed structure, an iron core, a silicate mantle, a thin crust, and a nitrogen-oxygen atmosphere, super-Earths come in an incredible range of compositions. Scientists group them into 4 main types, based on their density, which we calculate by comparing their mass and radius. First, there are high-density rocky super-Earths, similar to Earth, but larger, with iron-rich cores and thick silicate mantles. Planets like Coro 7b fall into this category. It is a rocky super-Earth with a surface temperature of nearly 2000 degrees Celsius, so hot it is covered in molten lava. Second, there are ocean worlds, super-Earths, where water makes up a huge portion of the planet's mass, sometimes 50% or more. These planets have deep global oceans, thousands of kilometers deep, lying above a rocky core. TOI 1452b is a perfect example, a super-Earth just 100 light-years away that is almost entirely covered in water. Third, there are mini-Neptunes, also called the gas dwarfs, which have thick atmospheres of hydrogen and helium, similar to Neptune but much smaller. These are at the upper end of the super-Earth mass range, and they blur the line between super-Earths and ice giants. Fourth, there are snowball super-Earths, frozen worlds, far from their stars, where all water is locked up as ice. though their strong gravity can create liquid water layers deep beneath the surface. This incredible diversity is what makes super-Earths so captivating. No two are exactly alike. One of the most important questions about super-Earths is their habitability. Could they support life as we know it? To answer this, we have to look at several key factors: their position in the habitable zone, their gravity, their atmosphere, and their geological activity. The habitable zone is the region around a star where temperatures are just right for liquid water to exist on a planet's surface, a critical ingredient for life. Many super-Earths orbit within this zone, especially those around small, cool, red dwarf stars, which are the most common stars in the galaxy. But habitability is not just about location. Super-Earths have stronger gravity than Earth, up to 3 times stronger because of their larger mass. This stronger gravity helps them hold onto thick atmospheres, which protect the surface from harmful cosmic radiation and trap heat to keep temperatures stable. It also supports more active geological activity, like plate tectonics and volcanoes, which recycle carbon dioxide and other gases, keeping the climate balanced over millions of years. On Earth, plate tectonics are essential for life, and super-Earths may have even more active geology because they retain internal heat longer than smaller planets. But it is not all good news. A thick atmosphere can also create a runaway greenhouse effect, like on Venus, making the surface too hot for life. Some super-Earths are tidally locked, meaning one side always faces their star, creating a permanent day side of scorching heat and a permanent night side of freezing cold. Others have no magnetic field, leaving their atmospheres vulnerable to being stripped away by stellar winds. Still, the potential for habitability is real. Planets like LHS 1140b, a rocky super-Earth just 41 light-years away, have all the right conditions: a rocky surface, a thick atmosphere, a stable orbit in the habitable zone, and a quiet host star that does not blast the planet with radiation. This world is one of the top targets for future studies, and it could be the first super-Earth where we find signs of life. Today, the James Webb Space Telescope, JWST, is taking our study of super-Earths to the next level. Unlike Kepler, which only found and measured the size and orbit of exoplanets, JWST can analyze the atmospheres of super-Earths, detecting gases like water vapor, carbon dioxide, methane, and oxygen signatures that could indicate life. JWST has already studied super-Earths like K2 to 18b, an ocean world, where it found water vapor and other organic molecules, sparking excitement about its potential habitability. It is also helping us tell the difference between rocky super-Earths and mini-Neptunes, a distinction that was nearly impossible before. Every observation from JWs gives us new clues about how these planets form, what they are made of, and whether they could be home to alien life. What makes super-Earths even more important is their role in understanding planetary formation. Our solar system's planets formed in a very specific way, with small rocky planets close to the Sun and giant planets far out. But super-Earths show us that planetary systems can be far more varied. They form quickly in protoplanetary disks, the clouds of gas and dust that surround young stars through the accretion of pebbles and rock fragments. Their composition depends on where they form in the disk. Close to the star, they are rocky. Farther out, they pick up more ice and gas, becoming ocean worlds or mini-Neptunes. Studying super-Earths helps us refine our models of how planets form, not just in our galaxy, but across the entire universe. As we look to the future, super-Earths will remain at the heart of exoplanet research. NASA and other space agencies are planning new telescopes, like the Plato mission, which will find thousands more super-Earths and study their stars in unprecedented detail. We will continue to use JWST to probe their atmospheres, looking for biosignatures, signs of life. We may even find a super-Earth that is almost identical to Earth, a true second home in the cosmos. These worlds are more than just planets. They are a reminder that the universe is full of possibilities, that our solar system is just one small example of the countless ways nature can build a world. Super-Earths are a testament to the power of human curiosity and innovation. From the first tiny wobble of a distant star to the stunning images and data from Webb, we have gone from guessing about exoplanets to studying them in detail. These worlds, bigger than Earth, smaller than Neptune, are rewriting astronomy, challenging our assumptions, and bringing us closer than ever to answering the age-old question, are we alone? The universe is vast, and super-Earths are one of the most exciting pieces of the puzzle. Every new discovery, every new data point, brings us one step closer to understanding our place in the cosmos. Please like, comment, share and subscribe to the channel.